Welcome to Math 1960. This is UNO Summer Session number 3. Today we're going to discuss integration of rational functions using partial fraction. So first we need to have a proper rational function. In each case of this, we need to have a proper rational function. That means if I have P over Q, the degree of P must be less than the degree of Q. So the polynomial in P must have a lesser degree of that of Q. So in order to have a proper rational function. So we have 4 cases here that we are going to discuss. First, if I have linear distinct factors in the denominator, I have to have a formula for that. So for instance, if I have, say I have P here over x minus a times x minus b, where a and b are not equal, then my decomposition would be in that form: a over x minus a plus b over x minus b. This is the way I can decompose of this polynomial function or this rational function. Also, there is a certain way of decomposing a function that is, that have linear repeated root. So if I have a function here, say this is P over x minus a, says to the third. So I'm going to have a over x minus a plus b x minus a squared plus c over x minus a. This is here, a here, a to the third. So this is if you have a repeated linear factors in your denominator. Sometime you may have a proper rational function that its denominator include irreducible quadratic factor. So say I have a say P over x squared minus a plus a, sorry, a squared plus a, say times x, for instance. Okay, so I want to decompose of this. This is irreducible quadratic factor. So I cannot reduce that into, I cannot factor it into into two linear factors, say, assume that. So then I'm going to say a over x plus, so here the degree is 2. Up top here I have to have a degree b, the degree has to be 1, plus c over x squared plus a. So this is how you factor, or this is how you decompose of a rational function with that contain a distinct irreducible quadratic factor. To integrate a proper rational function whose denominator contains a repeated irreducible quadratic factor, so when it's repeated, then we do something similar to that. Okay, Okay, we'll see everything here. So first of all, they asked me to integrate this type uh, of this function. This is a rational function. So the first thing I need to know is this rational function a proper rational function? So I said the proper rational function, the degree in the denominator must be greater than the degree in the numerator. But this is not the case here. Here I have x and there I have x squared. So this is not a proper rational function. It's improper. So in this time, when I have an improper, I'm going to use the long division concept. Here I have x squared, here I have x minus 1. So I would say x divided by x squared, I will get x. So x times x, that would be x squared minus x, x squared minus x. I'm going to change the sign, and then I'm going to sum. I'm going to have 0 here plus x. X divided by x is equal to 1. 1, this is x minus 1. I'm going to change the sign here, have 0, and then I'm going to have 1. So the remainder here is 1 because 1 divided by x is going to be 1 over x. So then my function I have here, function I'm going to be integrating would be this following function, x plus 1 plus a remainder, which is 1 over x minus 1. This is my integral. So when we integrate x, it's going to be x squared divided by 2 plus x plus ln of absolute value of x minus 1 plus c. So that is the integration of this improper rational function. So when we have a proper rational function, this is when we use the partial fractions decomposition. So just like we mentioned in our first slide, or second slide rather, that if I have a rational function that its denominator is two distinct factor or three distinct factor like this one, my decomposition would look like this: a over x minus a plus b over x minus b. So now my task is to find these numbers a and b. So the same thing, if I have three distinct linear factors and I have a denomination, I have a numerator that look like this, so my decomposition would look something like that. Same thing here, if I have a repeated linear factor px plus q over x minus a, my decomposition would be a over x minus a plus b over x minus a squared. Okay, and then if I have if I have combination of repeated root and distinct linear root here, so my decomposition will look like that. And then if I have irreducible root, so my decomposition will look something like that. We'll discuss some more in here. Okay, so in my in this problem here, first thing I'm going to do is just I'm going to say this is equals to x over, I'm going to factor this, so it's going to be x minus 2, x minus 3, times dx, right? Or dx. So that means x over x minus 2 times x minus 3, that is equals to a over x minus 2 plus b x minus 3. So if we multiply both sides with x minus 2 and x minus 3, then we're going to get x equals to ax minus 3a plus bx minus 2b. So that means we are going to equate factors of x together. So we're going to have 1 equals, because here the factor of x here is 1, so we're going to have 1 equals to a plus b, and then here I'm going to have 0 equals to 3a negative 3a minus negative 2b. So then we multiply. This is equation number 1, equation number 2. So we multiply equation number 1 by 2. So then we get equation number 3, which is going to be 2 equals to 2a plus 2b, equation number 3. So then we are going to sum up. So then we're going to have 2, okay, 2 on this side equals to negative 2a, negative a. So then a is equal to negative 2, and we're going to have b equals to 3. So from here my integration would be as follows. It's going to be integration of negative 2 over x minus 2 plus 3 over x minus 3 dx, and that should give me negative 2 ln of x minus 2 plus 3 ln of x minus 3 plus c, and that should be equals to ln x minus 3 cube over x minus 2 squared plus c. So that should be okay. Now we're going to discuss problem number 3. In problem number 3, we're going to have integral over of x x minus 1 squared. So that means we have 1 here, x minus 1 squared times x. So when we do the decomposition, we're going to have a over x plus b over x minus 1 plus c over x minus 1 squared. And then when we cross multiply with this, we're going to get 1